Okay, so here what we're going to do is we're going to prove angle-angle similarity. So let's write angle-angle similarity. And it basically just says that if you have two angles in one triangle congruent to two angles in another triangle, then the two triangles are congruent. So let's draw a picture of what this generally looks like. Here you have one triangle, triangle ABC, let's say. And you have that angle A is going to be congruent to angle D in this other triangle right here, DEF, and you have that angle B is congruent to angle E. Then you want to show that these two triangles are actually similar. So we want to demonstrate similarity here. The first thing I'm going to do is I'm going to say that we should convince ourselves that I could sort of like draw a diagram that looks like this. So I'm just going to call this point C, obviously, and I'm going to just draw a new diagram where I'm going to overlap the two triangles onto the bigger triangle. If the two triangles are the same triangle, then they're congruent and there's nothing to say. So if they're not congruent, then that means that one triangle is smaller than the other. So let's just say that ABC is the larger triangle and that then I have this other triangle here, DEF. Now, if the angle B is the same as the angle E, we should convince ourselves that this diagram is perfectly valid, where I'm just going to call the overlapping point at E. I'm just going to call it B now, and that this is D and that this is F, right? And then this is going to be C. So I've gone off the given that these two angles, this angle and this angle, these two angles are congruent, and we should convince ourselves that this diagram is perfectly fine. There's nothing wrong with what I did. These two angles will overlap. B is the same as E. A is the same as D, and that immediately guarantees that these two lines are parallel because these two angles are corresponding. Now, if we look at this diagram, we want to start sitting here and we want to say, okay, well, I mean, it's not necessary, but we could just immediately say that these two angles are congruent. So I have, so let's say, so excuse me, watch that out. Whoa, that these two angles are also congruent, right? So I'll put 3 ticks to illustrate that. But I mean, that's just good measure just to keep in mind that, obviously if you have two angles congruent in one triangle to two angles in another triangle, then by third angles theorem, these two angles are congruent. Angle F and angle C are going to be the same. But either way, you're going to have that these two lines are parallel. And what we do here is we make an argument using areas, okay? We have already that the three angles are the same. So by third angles theorem, I know that this angle is congruent to this angle. So what do I need to prove similarity? Well, I need that the sides are in proportion, right? So I'm just going to write that up here, that we want to show that, right, AB over DE is equal to BC over EF, and that AC is equal to over DF, right? This is what we want to show. This shows that the sides are in proportion and that the triangles are indeed similar, right? Similarity means that the sides are in proportion and all the angles are congruent. We have all the angles congruent, okay? Once we have two angles congruent, then we know the third angle is congruent, and then therefore all the angles are congruent. The only thing I need to show is this fact. So I have yet to show this. Now, how do I do this? I have to make an argument using areas. So the first thing that I want to isolate is I want to construct two new triangles. So I want to construct this triangle right here. So I want to draw DC in, and I have that triangle right there. And I also want to draw in, let's make it a different color. I also want to draw in this triangle right here, where I draw in AF. Okay, so we should see that I drew in these diagonals, AF and DC, and I'm going to be investigating ratios of areas in these triangles. So let's look at triangle DBF. And I'm going to be looking at the area of triangle DBF. So DBF, we got to isolate in our minds. We got to sit here, we got to take our time, right? Look at this thing and see what we have here. DBF is this triangle right here, right? So dBF, the area of this is going to be equal to, right? If you look, it's going to be dB times this altitude, or I'm going to call this altitude, so it's going to make it a 90-degree angle, and I'm going to call this H. Okay, so it's HF, the altitude, times the base is dB divided by 2. And if we look, okay, now let's look at the triangle that we just drew up, right? Triangle ABF, right? If we look carefully, right, its base is AB, and its altitude from this point is the same altitude. So it's HF times AB over 2. And something nice happens when I look at the division of these two. So the larger area is for sure ABF, right? So it's going to be ABF. Let's write it as the larger one over the smaller one, dBF. If you sit here and you take your time with this, right? Sit here and do this division, right? This one divided by the other one. Everything is going to cancel except for the fact that the ratio will be AB over dB. Okay? Did I do this wrong? Okay, right. Just remember that this is also point E, because I'm looking over here and I see that it's E as well. So we have to just be a little bit careful about what we want to show versus what we have here. That dB, this is point E that I overlapped onto B. So just know that this point is also E. So I could write that in there right away and just call it DE. Maybe it'll make it easier, maybe it'll make it harder, we'll find out. But either way, DE. Okay, look, this length, right? And this is the altitude. So base times height divided by 2 in this one, right? You have this ratio in this one, and then you divide the 2, you get this fact. Why is it that when you divide the 2, if you do the math, right, it's going to become times HF, or better yet, when I divide this one by the other one, so it's going to be this way. And you get 2, and then this is HF dB, and then this is going to cancel with this, and then the only thing you're left with is AB over dB or DE, whatever you want to call this point right there. Now, if you look, okay, if I draw this figure again so I could get a better picture as to what's happening, right? If I draw this again, where I have this, but this time I'm only going to be looking at this triangle. So let's look at this. This is F, this is C, this is again B/E, B/E, and then this point is again D. And if you look at the two triangles over here, right, if you look at this triangle again, the same DBF, right? And you look at this area, you can see that also there's some altitude here that goes like this, where this is a 90-degree angle. And let's call this point K, I don't know. You should see that it's dK, the area, times, right, this base, BF, divided by 2. And then the area of the other one that corresponds on this side is going to be, right, this area is going to, again, it shares that dK. So what is it? It's DBC, the area of DBC is going to be dK times, now this case is BC over 2. And again, you get that similar, when I do the larger one divided by the smaller one, I'm going to get BC over the area, the area of DBC divided by the area of DBF is equal to BC. So take your time with this, right? Dividing by this divided by that one, right? So we're going from this one to this one. It's going to flip this one, dK over BF. And then the dk's cancel, the 2's cancel, and you're left with BC over BF, right? And again, we could look at this as point E, or since we're looking at the other triangle, we could call this as the same thing as BC over BC over BEF, right? So, okay, so let's see. So it's BC over EF will be equal to this here, DBC, the area of DBC over the area of DBF. Now, if we look up here, so now I have this, right? These two. Okay. You should take your time in justifying these things. It's the same argument, but on like each side of these two triangles that I constructed when I drew in those lines. If you look up here, right, I want to show basically that AB over DE, this is equal to this. And if you look again, that just entails, right, since both of these, right, this is equal to this, and this one is equal to this one, right, we just need to show, since the area of DBF is the same on the bottom, the denominators are the same. If I want to show equality, right, I don't know if they're equal yet. I want to show that these two are equal, so I get this ratio being true here. If I want to show that, all I would need to show is that this is the same as this. I'm going to circle that again and convince ourselves that this needs to be the same as this. Now, let's try and justify that statement. I want to show ABF is same. The area of ABF is the same as the area of DBC. And how am I going to show that? Question mark, right? If I show that, then I've shown that this, right, is the same as this, which is saying that this is the same as this, which is the equality that I wanted. Okay? And then I'd have to do another argument to get the equality between these two. But okay, first one thing. First, we got to show that these two are the same here. And the way to do that, again, is if I show this is the same as this, then I'm done. So now let's look at the area of ABF. So first, ABF. If we look at ABF, right, we should see that triangle DEF is part of it. And if we look at triangle DBC, right, so D, B, right, that's point B, and C, right, we should see that DEF is also a part of that triangle. So the only thing I really need to show, if these two are the same, I need to then show is area of ADF, right? This piece, right? We should see that ADF plus DBF is ABF, right? ADF is same as, okay, and then let's look in the other triangle. The other triangle is this one, right? DFC. So if I show, right, that ABC is the same as DFC, right, then, right, it should be clear that then these two areas are the same, right? This would imply this, going back the other way. So just convince yourself of those statements, right? We could write out equations and we could show this, but you know, let's erase. Let's see. So let's write out equations. Let's illustrate this a little bit more slowly. Let's take our time a little bit more in case I lost you. So let's go back. Okay. So I want to show this here, right? I illustrated that the area of ABF over the area of DBF is equal to AB over DE. Okay, and I also showed that the area of DBC over DBF is equal to BC over EF. That was the argument that I just had made beforehand. Now, I want to show that these two are equal, right? I want to show that those two are equal. But that would equate to me showing that these two are equal. Okay? Showing that these two are equal, the denominator in both of these are the same. So I only need to show that these two things are equal. And then that's where I come up to over here. But if we look at this, let's look at ADF. Let's justify why it is that if I show this here, then I've shown this one. So ADF, it's equal to ABF, sorry. ABF is equal to ADF plus ADF. Oh, wait, is this right? No, it's equal to, what did I do? Okay, so ADF, this area, right? ADF plus DBF. There we go, DBF. DBF or DEF, whatever you want to call that point. And then I also have that DBC is equal to DFC plus DBF. So if, right, if let's say if I show ADF is the same as DFC, then these two will be the same, right? Like, just convince yourself in the diagram that should make sense. Okay, so this just equates to me showing, right? I need to look at what is it that I want to show. I want to show then that ADF is same as DFC. Okay, so let's look at these two triangles. So here's another diagram here. Let's get the picture again. So the picture again looks like this. So I have A, B, C, and then this here is D and F, and then I have this line and then this line. So I want to show, right, I know that these two lines are parallel, and that comes into play because if you look at this triangle, right, this is ADF, right, this triangle right here. If we look at this triangle here, right, we should convince ourselves that this line, right, serves as an altitude, okay, with base DF. So this is a 90-degree angle right there, and the base is DF. So what's the area of ADF? It's this line, whatever you want to say, whatever length that is. Let's, I don't know, M, right? AM times DF divided by 2 is the area of ADF. Okay, so this is the base, right? And the area of this triangle is that length AM, right? This is point A over here. Get rid of that C. AM is that altitude. If you rotate it the right way and see this. Now, similarly, if you look over here, right, we can convince ourselves that this line going up is the same as N, right? CN is the same length as AM. Okay, we can prove that, but we should just convince ourselves, like, if the two lines are parallel, right? And then I have this line being 90 degrees, and then this one's 90 degrees, this one's going to be 90 degrees, this one's going to be 90 degrees. We should convince ourselves that these two lines will be congruent. Okay? And we could guarantee that because of a parallelogram theorem. But okay, so in our case, we have that CN is the same as AM. And then that means that since, look, ADF, this triangle, right, is going to be AM times DF divided by 2. And then this one is going to be CN times DF divided by 2. But we just said that CN and AM are the same. So that means that these two areas are the same. And then that means that then this is the same as this, which means that this is the same as this, which means that then this is the same as this, which means then this is the same as this. And I've proven this equality here. Going back up the chain. To prove the next equality, this one here, okay, you make a similar argument, but you have to turn the triangle. So that way you do the same thing. So you do the same thing, but only on the different sides. It's a similar argument, but it's just on the same sides. And there's no reason to go through it again. Like if you have the triangle, right? And you draw the line like this now, right? You fit the triangle in over here. So it's A, B, C. And then instead, now this is D, E. And you make the argument again, and you'll show that this is the same as this, showing that the sides are indeed in proportion.